All right, so in this question, they are asking us to find all zeros, real and complex, for this polynomial x cubed plus 6x squared plus 6x plus 5. And this really is kind of the culmination of all the things that you guys have been looking at unto this point with positive and negative rational zeros, using Descartes' rule of signs, the synthetic division. So this is all kind of coming together to look at possible zeros and everything like that to figure out actually what some of these zeros are. So the first thing that we need to look for is we've got to figure out, okay, how many potential positive and negative zeros are there? So the way that we do that is we look at the sign changes and we see, okay, are there sign changes, right? So we look between the first term here and the second, there's no sign change, right? They're both positive. So then between the second term and the third, both positive, no sign change. Then the two last terms, they're both positive, no sign change. That means that for positive zeros, there are going to be 0 positive zeros, okay? So then the next part, and this is positive rational zeros and real zeros, I should say, not imaginary, right? So then the next part is seeing, okay, well, what about negative zeros? And the way that I do that, or that we'll do that, is we plug in this negative x and look at what happens with our sign changes after we do that. So we've got negative x cubed plus 6 times negative x squared plus 6 times negative x plus 5, okay? And now with these, I know that any odd degreed function, that's going to create a negative times a negative times a negative, which will be a negative number. So it's actually negative x cubed, okay? While even degreed functions, they actually will make a negative times a negative or some variant of that, right? Which means that the sign out front will not change, okay? So that's going to be a positive 6x squared, okay? And then this, the first power, that's an odd function, so we can just say positive 6 times negative x is going to be negative 6x, okay? And then we have our plus 5. There's no variable in there, so it did not change. So now we count the sign changes again, and we have from negative to positive, so that's a sign change, 1. From positive to negative, that's a sign change, 2. And from negative to positive again, that's a sign change, 3. So we can say that for negative zeros, there are going to be either 3 or 1 negative 0, okay? And so the way that we look at that is we say, are there zeros? And if it's 2 or greater, then we're going to subtract 2 from that until we get to 0. So like you can't take away 2 from 1, you'd have negative 1, and that's not going to be a viable 0. So we will have 3 or 1, and that's just because the way that quadratics work or polynomials work, they kind of work in pairs. Those zeros come in pairs. So when I'm looking at negative zeros, I'm going to have either 3 or 1 negative 0. I know that I'll have 0 positive zeros, okay? So when I'm looking at positive zeros, I'm going to have 0 of them. And so the way that I then figure out combinations of imaginary zeros is I look at my highest degree, which in this case, this cubic function is going to be a 3, right? And so when I'm looking at positive zeros, negative zeros, and imaginary zeros, they all need to add to positive 3 because it's a cubic function, right? So I know that I'll have 0 positive zeros, and if it's a x to the 4th or x to the 5th or so on, they would have to add to 5 or 4 respectively, right? And when I'm looking at those, I need to pay attention to how there are going to be more options, rather. There are going to be more combinations, right? In this case, I have 3 imaginary zeros or 3 negative zeros or 1 negative 0, right? If I have 3 negative zeros and I need them to add to 3, that means I'm not going to have any imaginary zeros, okay, because I already have all 3 zeros accounted for. So it could be that I have 3 negative zeros. However, if I have just 1 negative 0, okay, that means I need 2 more in order to make 3 zeros. And this is kind of the fundamental theorem of algebra, is that an nth degree polynomial will have n zeros. So if I have a 3rd degree polynomial, I need to have 3 zeros, okay? And they can be positive, negative, or imaginary. They also can sometimes go through through the origin of the graph, so 0, 0. But in this case, we're going to look at either having 3 negative zeros or 1 negative 0 and 2 imaginary zeros, okay? So now we've got to, so we looked at that using Descartes' rule of sign, or rule of signs rather, and now we've got to look at, okay, what are some potential zeros? Because now we know the number, the potential number of zeros, but now we need to say, okay, what are some actual potential options for us to find zeros? And the way that we do that is we look back up here at our constant term and at our leading coefficient, which is the coefficient to the left of the highest degree polynomial. Okay, and the way that I'm going to set up my potential zeros is I will take every factor of each of those, and I'm going to put the second over the first. So if this is P, let's pretend that's P, and this is Q right here, all my zeros are going to be all the options of P over Q. Okay, let me double check, make sure I said that right. Yeah, so when I'm looking at factors of 5, I know that 5 is prime, so the only factors are 1 and 5. Now I also know, except for I could have plus or minus 1 and plus or minus 5. Now my leading coefficient here also is on the x cubed is just a 1. 1 is also prime with just 1 and 1, so I'm just going to say plus or minus 1, okay? So with these options being P and these options being Q, my only options for zeros are going to be plus or minus 1 over 1 and plus or minus 5 over 1. Now, when I found out how many positive and negative zeros I have, I know that I will have 0 positive zeros, right, from Descartes' rule of signs. So I can actually just eliminate any of my positive options right here, okay? So now my only options for negative zeros are going to be negative 1 over 1 or negative 5 over 1, okay? So the way that I'm going to determine if this is a 0 is I'm going to plug each of these in, so negative 1 and negative 5, using synthetic division. And if I get a remainder of 0, that means that I will have that will be a 0, rather, okay? So I'm going to try negative 5 first, partially because I mean, you can start with whatever you want, but in the multiple choice options of this problem, it has negative 5 as a potential 0. Okay, that's one of the options. So I'm going to just kind of try that. So when I'm doing synthetic division, I need to look at the function and I take the coefficients of each of the variable terms, right? So I have variables of x cubed, x squared, x, and the constant. Okay, so I'm going to take the coefficients, which on the x cubed is just a 1. I'm going to take the coefficient of my x squared, which is 6. I'm going to take the coefficient of my x, which is 6. And this is from the original function, not the p of negative x or anything like that. And then I'm going to take my constant, which is 5. Okay, and so this is now synthetic division. I'm going to bring I'm going to bring the 0 that I'm checking to see if it really is a 0. I'm going to bring that out to the left side here. And now I'm going to complete synthetic division. The way that I do that first is bring down this 1. Okay. I just bring that straight down, and then I'm going to multiply back here. And when I multiply, I put whatever I multiplied right below the second column. Okay. Then I'm going to add straight down. Okay. So 6 plus a negative 5, that's a 1. Now I'm going to multiply again, okay? And then whatever I get is I'm going to put right here. So you can kind of see this pattern that's happening. So 6 plus a negative 5, I'll add those again, that's 1. Interestingly enough, I'm going to multiply one more time, negative 5, 5 minus 5, that is 0. So with this being 0, that means that negative 5 is in fact a 0 of my function. Okay, so negative 5 is a 0 of my function. So now what we've done is we've actually done a little bit of division. So previously, these were 1x cubed, right? 6x squared, 6x. When I do this synthetic division, though, I'm actually dividing out one of the 0s, which takes away one of the degrees of our function. So now if I were to replace some of the variables, I would have 1x squared, 1x, and 1, okay? And in between these, I can just put my original signs. Sometimes it'll be negative, right? If we subtracted and it was less than 0, it would be a negative. But because all these were positive numbers, I'm going to have x squared plus x plus 1, okay? And now, interestingly enough, that is actually going to be how we'll find our other two zeros, okay? So because I know my options are either, if I look back up here, my options are either 3 negative zeros or 1 negative 0, and I only have one other option for a negative 0, I know that I couldn't really get to 3 negative zeros. So I'm going to stop trying now through other synthetic division or whatever method you might have. You could also try factoring if you wanted to. At this point now, since we're at a regular quadratic, not just a polynomial, you could try to factor it. This one won't factor though. So what I'm going to do is I'm actually going to use the quadratic formula here to find my last two zeros. And this works anytime you get back down to your original quadratic of an x squared plus x plus whatever, right? So now that I'm in this x squared realm, I can actually use the quadratic formula. So even if there are actually more negative zeros, I will find them because I'm now in a quadratic. I will find them by plugging them into the quadratic formula. So here, let me switch back to white. So the way that we'll do that, remember the quadratic formula is x equals negative b plus or minus the square root of b squared minus 4ac. It's kind of a shady a there, sorry. And this is all over 2a. Okay, so what I'm going to do is I'm just going to plug and chug, remembering that in a quadratic, we're in standard form of ax squared plus bx plus c, not 0c. And so here's my a, here's my b, and this constant here is my c. Okay, so I'm just going to plug all these in and solve this thing, right? So I've got x equals negative 1. It's kind of tricky when they're all ones, right? Plus or minus the square root of 1 squared minus 4 times 1 times 1. Okay, and I'll simplify that in just a minute. All over 2 times 1. All right, so now my next step is going to be x equals negative 1 plus or minus the square root of 1 minus 4, which is actually going to be negative 3. So I can just go ahead and put that in now. So plus or minus the square root of negative 3 all over 2. All right, so now that I've got the square root of a negative number, we've got to think, what does the square root of a negative number actually come out to? And in our study so far in this module, we found that the square root of a negative number is actually an imaginary number. So I have x equals negative 1 plus or minus the square root of 3i, okay, because I took the square root of the negative 1, which is I, and I'm going to put that all over 2. All right, so now these are two more zeros. Remember, this is representing two numbers because I have this plus or minus. So these are imaginary zeros, right, which now this satisfies up here. We're actually in this realm right here where we've determined now that I have one negative 0 and I have two imaginary zeros, and there they are right there. So when I'm looking at that problem, I have one negative 0 at x equals negative 5, and I have two imaginary zeros here at x equals negative 1 plus or minus the square root of 3i all over 2. All right, I hope that helps.